Hello, my name is Lohit, and today we are going to be talking about cryptography and quantum computing. Specifically, how quantum computing affects cryptography. You might wonder, why is this important? The reason is cryptography helps defend some of the world's most important systems. For example, when you pay for something using your bank account, credit card, or say an ATM, you are making a transaction. A transaction has data that needs to be protected from hackers. The act of protecting this and hiding it from them is called cryptography. So, now, why is quantum computing important to this? Quantum computing is simply just regular computer science, but with a twist in that data is stored inside of these special subatomic particles and they are called qubits. Qubits have interesting properties that are mathematical that we are not talking about because that's just no. But we will still be discussing how they affect cryptography. So I'll explain what our best non-quantum cryptographic methods are in the next section. I'll see you. So, as we were talking about in the previous section, now we are going to look at RSA, which is an algorithm that is used widely in the modern day to protect information from eavesdroppers. So let's see what this entire algorithm is about. So let's say we have two friends, Alice and Bob. And let's say we have a third person, Eve. Alice and Bob are planning a prank on Eve. Eve wants to know what the prank is about. So what does she do? When Alice and Bob are texting each other, Eve hacks into their app and manages to see their text for herself. So let's say that the text is a number, M. You might wonder how we can convert text into a number first off. The answer is ASCII. ASCII is a text to number conversion standard used in computers. So, now, what Alice can do is, she can create a pair of keys. In this case, it's not Alice that's doing it, but Bob. What Bob does is, he creates a public key and a private key. The public key is like a lock. You can lock any messages with that lock, but you can't unlock them. The private key is the key to said lock. The key in the private key won't work with any other public key, and public key can be unscrambled by any other private key. So let's call the public key E and the private key D. So in this case, Alice has a message M, and what she does is, she does something with E to it. So after she does something with E to the message, it becomes a cipher, C. The cipher goes to Bob. Bob has D, which can decrypt ciphers. After he decrypts the cipher, he gets M back. Eve does not have the ability to decrypt the cipher though. So she only ends up having the cipher. So the main technique and genius in RSA is how these keys are created. How are they created? Let's find out. Okay, before you get scared of the maths and run, it's very simple comparatively. There are two values here that are important, P and Q. P and Q are two prime numbers, which means that they can only be divided by 1 or themselves. If they divide by any other number, they get a fractional value. So, now public key gets chopped into two halves because of this, N and E. N is simply P times Q. That's easy. But E is a co-prime of phi of PQ. What? So, what is a coprime? A coprime is a number that does not have the same factors as any other number. For example, take 8 and 15. So, 8 factors are 2, 4, 1 and 8. 15 factors are 3, 5, 1 and 15. The only factor that they both share is 1, which is shared amongst all numbers. Therefore, 8 and 15 are coprime. So, E is coprime with another number, the phi of PQ. What is phi? Phi is a function which takes in a number and then outputs another number. What function is it? Euler's torsion function. Why is there like 70 different Euler torsion functions? It's because that guy is too good at maths. The reason he has a mortal lifespan is because he's that good at maths. So, the torsion function of two prime numbers multiplied, PQ, is simply P minus 1 times Q minus 1. So, if you have a number that's coprime with that value, you can create a public key. Now, how about our private key? Our private key is equal to, follows the equation, DE is equal to exactly 1 mod phi of n. That's a lot of new things. First off, what is D? D is a private key we're trying to find out about. E is the coprime of the phi of the PQ and whatever. Now, what is a mod? A mod is also known as modulo. It's simply the remainder of a division. That's it. So, for example, 8 mod 3 is 2, because the lowest multiple of 3 is 6. The closest multiple of 3 is 6. You might ask, what about 9? But 9 is greater than 8. So, yeah. So, in this case, we have 6. 8 minus 6 is 2. So, there's 2 left over if we try to divide 8 by 3. So, in this case, the modulo of phi of n. What is phi of n? N is PQ. So, it's just the phi of the PQ of the etc. of the etc. If you know P and Q, this entire equation is very easy to convert. But if you don't, it's a complete pain. Now, how do you encrypt and decrypt messages with this? The encryption rules are C, the cipher, is equal to m to the power of e modulo n. Now, how do you decrypt it? The decryption is even worse. It's c to the power of d times e is equal to m mod n. So, that's how you decrypt the public and private keys from two prime numbers. But just a question you ask. Why can't you just reverse the entire equation and find D, which is the private key that you're not supposed to share, from E and N? The answer is that because of the modulo, a lot of critical information is lost. Because all this critical information is lost, even if you have N and E, the best option for D is simply to try different values of D until you finally find the correct answer. Or, which is the more efficient way, which is to try different values of P and Q that give different values of N and E. And then you can just get D from that. So, that is RSA. So, now let's get to quantum computing. Now, the slide in front may look a bit intimidating. There are 4 balls at the bottom. There are a few symbols like this above them. There are 3 lines with a bunch of H's and pluses and lines connecting them. But let's explain them one by one. First off, the balls. The balls, if you notice, have an arrow through them. The arrow represents a qubit. You might ask how that works, because a normal bit is just 0 or 1. It's a binary numerical value. The answer is that a qubit is what is called a 3-dimensional spinner. 3-dimensional makes sense. After all, it's in a 3D ball. But what is a spinner? A spinner is a complicated physics concept that was basically invented for quantum mechanics. It involves basically being the square root of vectors, and it has Grossman numbers, etc., etc. But remember, this is not maths. This is quantum cryptography. So let's just say that a spinner is a vector with a fancy name and fancy math. When the spinner is pointing straight up, it's at a state of 0, or more accurately, ket 0. The line and angle are called kets. It comes from bra-ket notation. The opposite of a ket is a bra, which looks like this. So this is bra-ket notation or Dirac notation. So you could call it ket 0, 0, state 0, qubit 0, basis 0, anything. I'll call it 0 ket or ket 0. So when it's pointing straight up, it's ket 0. When it's pointing straight down, it's ket 1. Now there are still 6 of these, and we've just explored 2 of them, up and down. So what is front, back, left and right? Front is called ket plus. Back is called ket minus. And left and right are called ket clockwise and ket counterclockwise, but no one really uses those a lot. And we won't be using them for this presentation, because we're covering BB84, which only uses these 4 states. So now the thing you see above them is a quantum circuit. Each of the lines represents a qubit, like one in the balls. And each of the squares and circles represents a gate. The black gates are for measurement, and the gates that aren't black are meant for quantum wibbly wobbly stuff. How does these gates work? Let's find out. So now this might seem even more confusing than the first image, but trust me, it's kind of easy to understand once you figure it out. So first, let's begin at the top left. On the top left are the 3 polygates, the X, the Y and the Z. These correspond to rotations across the X-axis, the Y-axis and the Z-axis. So the most commonly used one is called the X gate or the NOT gate. You can see the black circle around the block sphere. The circle represents the direction in which the X rotates. The X rotates 100 degrees, 180 degrees in the direction. In this case, it's called the X because it rotates around the X-axis. Very creative naming. We can tell that this was made by physicists. So then there is one other type of gate that we need to know about, the Hadamard. The Hadamard corresponds to a reflection, like a mirroring. What's special about it is that it's at a 45-degree angle between the X and the Z axis. So for example, if this is the X axis, this is the Z axis and this is the Y axis, then this is what the poly X gate rotates in, and this is the line of reflection with the Hadamard. It goes front, up, down and back. So what this does is, it turns a ket 0, which goes up, into a ket plus, which goes sideways. It turns a ket 1, which goes down, into a ket minus, which goes back. And because it's a reflection, it can also do vice versa. So what is special about these states is that when you measure a qubit, which we will get to, you reduce it to either a ket 0 or a ket 1 state. The other states, they have a set probability to get into one of these states. The plus, the minus, the clockwise and the counterclockwise have a 50-50 probability of becoming a plus, 0 or a 1. This will be important. Hold on to that. Now there is one more gate that is nice to know about. It's called the controlled X or the control NOT. What it does is, it controls two qubits. One is the control qubit and one is the target. The control is the one with the dot and the target is the one with the plus. You can see this gate in the bottom left. So when the control is 0, nothing happens. But when the control is 1, the other qubit also gets flipped. So it behaves like a poly X gate only if the control qubit is equal to 1. Why is this important? Let's look at a circuit and find out. Now the code is even more intimidating than the drawings. But don't worry, the code is just my computer being obnoxious. So the first 4 statements, the froms, are just initializing the whole quantum stuff, like adding the little tools that help you work with the quantum circuit, etc., etc., allowing you to run the quantum circuit, etc. So now below that you see QC equals quantum circuit of 2. This creates a quantum circuit with 2 qubits. Now then you see QC.H. The H is for Hadamard. So if the qubit starts off as 0, which it does in this case, it turns into a plus, and if it's a 1, it turns into a minus. In the circuit, all qubits start off as zeros, by the way. And then we have a control NOT, that's a plus, that is controlled from Q0 and goes to Q1. Now if you think about it, it gets kind of confusing here, because a control NOT assumes that your variable is ket 0 or ket 1. But here, because you use a Hadamard, it's a ket plus. What does it mean? It means that since the ket plus has a 50-50 chance of being 0 or 1, the qubit Q1 that's being controlled also has a 50-50 chance of being flipped. This state is called superposition. But one important thing to note is that if Q0 is 0, Q1 must also be 0. And if Q0 is 1, Q1 must also be 1. They can never be different, because that violates the rules of the C0. This state is called entanglement. The specific form of entanglement is called the Bell state. So then lastly, the QC.draw MPL simply means that it should draw it in the fancy style. We are not going to use the fancy style when you get to BB84. Now the lower one looks very similar. The first 2 gates are the same as the upper one. Now you might wonder what the sampler is if you look closely at the code. That will be explained. So as the top one was a Bell state, the bottom one is called the GHZ state, or GHZ state if you're Canadian or British in general. So it has 3 qubits, but there's also a 4th line that has 2 lines. This is the measuring line. It's where your measurements go. As I mentioned, the measurements collapse a qubit to 0 or 1, and each different arrow has its own probabilities for where it will collapse. And then the collapse values are collected up in the measured duct. So, the only difference between this and the Bell circuit is that we are measuring, and that there is a third control knot from Q0 to Q2. This does the same thing as the first control knot, and it means that all three of the qubits are in superposition. So it's either 0, 0, 0 or 1, 1, 1. So in the code, you can see there's a second C naught, which can be used CX as well. And then there's a QC of measure all. That's what the measurement boxes are from. Now, the sampler, it basically runs the circuit several times. Of course, I don't actually have a quantum computer at home, but we can still simulate it using random number generators. So, sampler runs the circuit several times using these classical methods, and then it collects all the different results. From this, it can calculate the probabilities. Now, if you look down at the probabilities, it shows what we expect. There's an 0.49 repeating probability of getting a 0, 0, 0, and a 0.49% probability of getting a 1, 1, 1. This is as expected. So that's the basics of working with Qiskit. Now, let's talk about Shor's algorithm. So, as mentioned in RSA, we need to figure out P and Q to find N, E, and D. But one important thing to note is that N, which is shared to everyone across the network in RSA, is public. And it also has P and Q as factors. Now, you can factorize N to find two prime numbers. These numbers are P and Q, and from that you can reverse engineer the entire key. Think of this as picking the lock. If RSA is public, Q is the lock. This is a strategy that Eve can employ, but it's very slow because, as also mentioned in RSA, you have to constantly try out new ideas and new values because there's no set formula to find them. This was the norm until quantum computers came along. What do quantum computers do? Let's see. So, there is a massive algorithm that we are not going to be able to explain in time, but it's very interesting, and each part of it itself is worth a read. It's called Shor's algorithm, and it's actually not meant for code breaking. It's a fancy factorizer. But for RSA, the factorizer helps with the code breaking. So this is Eve's lockpicking method. This is a few details on the diagram. The H's again represent Hadamard's. So every qubit is in a plus state except for the last one, or the last ones, which go through a bunch of U gates. A U gate is a rotation across an axis some amount of degrees. So after going through several U gates, controlled U gates in this case actually, this entire state is an entangled mess. Now what you can perform is called a quantum Fourier transform. For people in signal processing, this is a big deal. For people in quantum mechanics, this is also a big deal. For people who are in quantum signal processing, this is the biggest deal. So, the QFT, or rather the inverse QFT, because it's a -1, allows you to figure out the factors eventually. It's not perfect, it isn't a set formula, but it's much faster than any other method so far. The inventor of this method, Peter Shor, was actually, this was kind of his big break. He became a big deal when this happened. And there was even a story once where he got randomly interviewed by an NSA guy in the middle of a conference, because this is national security wise, because even the governments use RSA. But if this is a breakthrough, this noteworthy, can we fix it? Let's see. So now let's do a demonstration of a quantum encryption technique, which is called BB84. So let's say for Eve's birthday party, Alice and Bob are planning a prank and a surprise for April Fools. So now Alice's message is something funny. Okay, Eve is gonna get trolled. So now what Alice does is she generates a list of two random numbers, Alice key and Alice orient. Now key is the data she wants to send to Bob. Not as in the message, but just some data. Now the orient is in which axis she is going to send it. Because if you look at the block spheres at the bottom, you can see that 0 and 1 are on the z-axis, but x and y are on the x-axis. So Alice orient, when it's set to 0, is on the z-axis, and when it's set to 1, is on the x-axis. Alice key determines whether it's going to be top front or bottom back. So that's what Alice key determines. So from Alice key and Alice orient, there are 4 possibilities. 0, 0, which is get 0. 0, 1, which is get plus. 1, 0, which is get 1. And 1, 1, which is get minus. All of this is happening from Alice's perspective, by the way. So let's see what happens next. So what Alice does is she encodes this information into a quantum circuit. How so? If Alice key in the specific bit that she is encoding has a 1, then she flips the bit using the x. And if Alice orient has a 1, she flips it from z to x using the Hadamard. So this leads to some set of x's and h's. Let's see what happens next. So now we switch to Bob's perspective. Bob just got this set of qubits from Alice. So what he does is he doesn't know which ones are in the x-axis and which ones are in the z-axis. And his measurement is always on the z-axis. So what he does is he randomly measures them on the z-axis and sometimes on the x-axis. The specific details are that he converts the x-axis back to a z-axis using a Hadamard, yada yada yada. We don't need to know that. But he just picks randomly whether he wants to measure them x or measure them z. So this is what our circuit looks like now. So what does Bob do after that? Now, from the measurements, he would get a list of measurements. The code here looks a bit wonky and comment-filled, mostly because Qiskit does not, for some reason, have the ability to run a quantum circuit once and only once. It only has the ability to sample probabilities. So I improvised and decided to just use a classical approximation. So now we have a set from the quantum circuit. Now a special thing about this is that if Alice has set the qubit on the x-axis and if Bob measures it on the x-axis, the value will be correct. If Alice has set it on the z and Bob has set it on the z, the value will be correct. But if they disagree, then Alice's value has a 50-50 chance of going either way. And because of that, the data inside of the bit is garbled and lost. This is how the data is protected when it's transmitted across the public web. So from this, Bob gets some real, some fake bits. Now Bob has to clean it up. Let's see how he cleans it up. Okay. Now, this is happening from both Alice and Bob's perspective because they're working together now. So, now, what Alice and Bob do is, they say, okay, so these are the orientations I picked. So these are the orientations with which I set the qubits for Alice, and these are the orientations with which I measured them for Bob. So now they say, okay, so this is what the other guy used. Does it match with mine? When it doesn't match, they know that there's a 50% chance that that qubit is fake. So they discard it. But if it matches, they know that the data matches on both sides for sure, 100%. So they can keep it. Now, this resulting data is our key. Now, we can use this key to encrypt and decrypt messages, can't we? Wrong! What we have to do first is check if Eve has been up to something silly while we were in the middle. If you're wondering, Eve cannot just copy the qubits and then use the correct measurements when Alice and Bob send them out. The reason for this is a no cloning theorem, which is another piece of math. Oh my god, why is there so much math here? But in the end, it says if you copy a qubit, the original qubit will be destroyed. So the qubit basically teleports. But there cannot be two copies at the same time. It's physically impossible. So because of this, the only option that Eve has to be able to measure the qubits is to directly grab them from the stream before Bob does, try to measure them, and then drop them back in like nothing happened. The issue with that is, when you measure it, you set it back to a certain angle. But Eve doesn't know what the angle is yet. And because of that, she can set it to the wrong angle. If she sets it to the wrong angle, some data is lost, just like when Bob measures it. And because of that, Alice and Bob may disagree. To be specific, let's see what happens. What they do is, they share half of their qubits. The same half. In the program, it's every other qubit. If these match, then Eve has not been up to anything. But if they don't match, then Eve has probably measured the qubits before Bob got them, and that means that they need to try again, because Eve possibly has the qubits' actual values. Now finally, let's see how we can encrypt and decrypt with the keys. This part is classical. We're in the home stretch. So, now we have Alice's message and we have encrypted it. How do we encrypt it? If the key is set to 0, then we leave it unchanged. But if it's set to 1, we double the value of the letter. This is not how the actual encryption process would work, because that's too simple and crackable. But this is just a simplification, so let's use simplified encryption. This key is not like the RSA public and private key. It is a two-way key. So Alice and Bob both have the key, and they can use it to both scramble and unscramble their messages. So Alice scrambled it with her copy of the key, and Bob can unscramble it with his copy of the key. And now we have what we were asking for. A way to scramble and unscramble without the key or the text being shared. Lastly, let's see what Eve's perspective is. So, Eve can see the measurement angles that Bob has sent, the qubits that Alice has sent, but she can't interact with them. Alice telling him where he was wrong with the measurement angles. Half of the security key that Alice and Bob made. And Alice saying, okay, Eve isn't watching us, it's safe. And then they just send some random encrypted garbage. That is all Eve knows. Eve does not know how to decrypt it. Eve does not know what they used. Eve does not know anything. Mission successful. Now, let's see an actual visualization of how it works in Jupyter Notebook. So what we are doing here now is we want to encrypt the text Eve gonna get trolled. We need a random number generator for this as well. So first we generate two random lists, Alice key and Alice orient. So let's generate them. So Alice orient's purpose is to determine whether it's oriented xyz or zyz. 1 is for xyz, 0 is for zyz. Now Alice key is determining whether it's a 0 or a 1 that's encoded in. That one is simple. So first, if there's an Alice key, we need to flip the bit. So we add an X or a naught. And if Alice orient is there, we need to use a Hadamard to get it to the x-axis from the z-axis. So we add a Hadamard if Alice orient is on 1. So now this is what our circuit looks like. Now you can see clearly that there are 4 types of possibilities. 1 0, which is x, 0 0, which is nothing, 1 1, which is xh, and lastly 0 1, which is h. So these correspond to the different basis vectors such as 0 kit, 1 kit, plus kit, and minus kit. Now Bob is measuring all the qubits. To help structure this, we have added a barrier between Alice and Bob's sections, which looks sort of like a straight line. So now on the left side we have Alice's side, and on the right side we have Bob's. Bob randomly picks whether to use it as an x-axis measure or use it as a z-axis measure, and he randomly picks for each qubit by Hadamarding it if he wants to do it on an x-axis measure. So after he does that, this is what the circuit looks like. Now here there are also 4 possibilities. So we will look at those 4 possibilities later. And you can see most of the time it's random, and the diagonal row of cells is just the measuring cells. Now this stage is where it gets a bit wonky because I couldn't exactly simulate the circuit exactly once, so I had to improvise with the classical system, and that's what I did. So now if Alice's orientation and Bob's orientation match, that means that Alice set it the one way and Bob measured the same way, so the data is stored. But if they don't match, then the data gets scrambled. For example, take a look here. There are 2 Hadamards. Therefore, Alice measured it on an X, and so did Bob. Up there's only 1 Hadamard on Bob's side. So Bob tried to measure it on X, but it was actually a Z. This caused an issue, as you will see. Now you can also see here that there are a few other issues like that. Now the issue with this is that when you measure it incorrectly, you end up having a 50-50 probability to get a false answer, which causes the data to get scrambled and to disappear. The reason for this is that the plus and minus vectors are within the circle, and they're at the midpoint between the 0 and the 1 vectors, which means that it's a 50-50 chance to see where it goes. So this area is for interference, which you will get to. So now let's print the list. On this list, some of them are false and some of them are true. Now we need to find out what was false without sharing the actual list. What Alice and Bob do now is they share the orientations they picked. If they share it, they can tell, okay, Bob used the wrong orientation, so his qubit might be false. Here, Bob used the same orientation as me, so his qubit must be true. So we can discard all the possibly false qubits, as is shown here. The false means that Alice and Bob have differing measurements, and true means that they have the same orientation. If it's true, that means that the bit is valuable and not garbage, and we can still keep it, which is why the list is significantly smaller than it used to be. So now, we need to check for eavesdroppers, because an eavesdropper can actually take the bits from the stream and they can measure it to try to find out the value. They cannot copy the bits because of the no cloning theorem, but they still can take them from the stream and measure them. So what both sides do is they share half of their bits with each other. If the bits match, all of them, then it's alright. But if they don't match, that means that it might have been measured twice, which can cause an error. For example, you can see here that one of the bits is flipped, one of the bits that we are measuring. So this causes the next bit to also be flipped and this bit is a trustworthy one, so it matters if it's flipped. So now what we do is we send it to this eavesdropper or tampering check, and you can see that it throws an error at you. This is why you need the check, so that if an eavesdropper comes along, you can tell that something's up. So now let's comment that line back out and continue like nothing happened. So lastly, we need to encrypt and decrypt it. We're in the home stretch. So to encrypt it, all Alice does is she adds 2 to all of the values. So if the value is 0, that means that it becomes 2. And if it's 1, it becomes 3. And then she just multiplies. So if there's 0, the message's ASCII value gets multiplied by 2. And if it's 1, it gets multiplied by 3. This causes a complete garble. Now Bob can unscramble it by just dividing by the same number, and he gets a message back. Lastly, let's see things from Eve's perspective. From Eve's perspective, all she can see is the qubits that Alice and Bob are sending, the angles that Bob measured them at, Alice telling him what the wrong angles are, the half of the key that Bob made, and Alice saying, okay, Alice and Bob are safe, Eve isn't watching. And lastly, the encrypted garbage that Eve had to read. So this is what it looks like printed out on the screen to Eve. As you can see, it's worthless. Mission accomplished. So, we have just gone through an entire journey. From learning about RSA and modern day cryptography, to learning about quantum computing and why it's funky and weird, to learning about how quantum computing can break RSA, all the way to how it can create new methods that are better than RSA. What does this mean for us though? It means that quantum computing is a double-edged sword. It can both be used for good, like creating new encryption methods and learning about new medicine and figuring out experimental physics, and it can be used for bad, like for example causing DDoS attacks to occur and hacking into other people's security. But there is one important caveat note here. Quantum computing is not fully developed yet. It has a lot of limitations. For one, it cannot be big. Qubits are hard to keep in a single state at a time. They like to what is called decohere. Decoherence means that the qubit randomly just bumps into something and changes its state. Think of it as the block sphere. It hits something and then all of a sudden the arrow rattles around like a marble in someone's head and goes somewhere else. So, how does thus cause BB84 to be unimplementable? The answer is, first off, transmission. Transmitting quantum signals across a wire itself causes lots of decoherence opportunities. Bumping into the wire, bumping into other particles, bumping into yourself, bumping into the air, anything. But you can still see the potential from here. If quantum mechanics and quantum computing manage to properly mix together, and quantum computing manages to grow and become a better version of itself, then it can truly be a use of the double-edged sword. As to what I learned from this, I learned how to use Qiskit, which is a library that I use, as I have mentioned before, to work with quantum circuits. I also learned how to be flexible when programming, because there are quite a few situations where a Qiskit wouldn't have the correct tools or capabilities yet to do what I wanted it to do. And I managed to pull through with it. I still find it very interesting that I managed to do this in 3 days, and specifically the programming in 1 day. But overall, I found it a fun experience, and I hope I can continue doing this in TKS. Stay strong.